Oh, welcome back, everyone. So glad you're here. I want to again thank the students who spoke this morning. I went, I can't be everywhere, but I went to the talks I went to were excellent. I'm really, I think you should all be proud of yourselves. Let's give a round of applause for the student speakers. And also to remind the student speakers to be sure to, if you haven't already, to go down to the Math Skills Center and choose a new book for yourself. Unlike the ginormous book giveaway, those are all old books, but there are new books that you can choose whatever one you like. So we're pleased to be back again this morning with Talitha, with Dr. Washington. I'll be professional here. Yeah, her title, I read the title and I thought, yeah, we're always happier when the world is linear, right? Derivatives are easier, you can graph, all of that calculus stuff. And then they say, but it's not. The world is not linear. And so now what are we going to do? So fortunately, there are people like Talitha who have thought about ways of thinking about real world problems, especially when the real world is not conveniently linear. So she's going to tell us about nonlinear finite difference schemes for a nonlinear world.
Thank you. Fantastic introduction. That was just awesome. Okay, so here's my disclaimer that the material is based off of the funding opportunities from NSF, but all of my expressions are my own, and don't represent any organization. That's, And we also have a new building at NSF. It's really cool. Has anybody been to an IKEA store? It's kind of like the building inside, so it's really like new. We've only been in there 2 years. There's a gym, and it's fantastic, yeah. It's good times. So so it's chopping off the top of the screen, so I'm not sure exactly. Let's see if we can, is this better, kind of? Can you still see it? Yeah. Okay, right, so I'm a mathematician at Howard University. We're federally chartered, so we're started by an act of Congress. Private, historically black university located in DC, not too far from President Trump. And we were founded in 1867. We were the only historically black university as designated as R1. Now, when they did the Carnegie reclassification, we became an R2 institution. In my department, we have a PhD math program, which was established in 1976. We have a total enrollment of 9,392. We have graduate and professional studies. So a whole hodgepodge of things. So where did I start? Right, so this is what I call my mathematical beginning. I went as an undergrad to Spelman College. I took calculus in high school, and I tested into pre-cal 2. I was like, oh, really? Thanks, right? And then the second semester, I took, well, this is analysis they call it, that's calculus 1. But I also took this Foundations of Math, which is the introduction to proof writing. I'm not sure if they have that course here, yeah? It was hard. You see what I got here, a W? Because I didn't want that W to be an F? Right, yeah. So it was very challenging in the first year, but as I was having breakfast over at the guest house, I was overhearing some gentleman talking, and one of the gentlemen said, we serve a God who gives second chances. So I took that course the following year, and I made an A. And then I made an A in all of my math courses, except like 2, I made a B. So it wasn't that math always came easy. I had to really work at it, but I also enjoyed the challenge along the way. This is me as an undergraduate here, where I presented a poster on our science day back in 1995 on the stability of difference equations. So just looking at difference equations, when are they stable, when are they not, which really laid some of the groundwork for what I would do like decades later. I had absolutely no idea. The gentleman I'm standing with here, this is Dr. Ronald Mickens. He's a professor at Clark Atlanta University. Literally, Clark Atlanta is right across the street from Spelman. I knew him as an undergraduate student. He even gave me his book, and I was like, thanks. And I kind of put it on the shelf, and it collected dust. What happens decades later? I invited him to campus when I was at the University of Evansville, and we started doing research together. So the moral of the story is, be nice to your professors, because they actually could be your collaborators. You never know. I went to graduate school at the University of Connecticut, and when you go to graduate school, when you do undergrad, you take the courses, I'm done. You do a thesis, they say, cool. When you go to graduate school in the first couple of years, like maybe equivalent to master's, you do the same thing. You still take some courses, you may do a thesis. But when you go for the PhD, the question becomes, what are you going to contribute to the current body of knowledge? And is that contribution going to be important? And how is your trajectory going to look moving forward? So it's way more subjective than checking a box. You have to convince a committee of people that your new knowledge that you are generating is actually good and valuable for the community. So when you're trying to figure out what should I do, for me, I was very torn. I wanted to do mathematical biology because that was cool and hot at the time. But then I also, Dr. John McKenna, he looked at the oscillations of the Tacoma Narrows Bridge. Just kind of, what do you do? So what happened was I looked at protein interaction model under Dr. Choi, and then Dr. McKenna, he was more of my mentor. So it was really nice in graduate school. I had a mentor and a research advisor. So it's the best of both worlds. So here's, let's consider an example of numerical instability. So if we look at the popular decay equation, dy dt is equal to negative y, with y of t naught equal to y naught, we can solve this exactly. Do your favorite thing, either separation of variables or whatever. And so the exact general solution is y of t is equal to y naught e to the minus t naught. We can actually discretize the dy dt just using a forward Euler scheme. And we talked about Euler in the Hidden Figures movie, right? So here it pops up right here. So we replace dy dt. Here's our change in y sub k plus 1 minus y sub k. And our change in time, our delta t, we can rewrite that as just h. Replace the y on the right-hand side with y sub k. So here's a way we could discretize to go from y sub k to the y plus k plus 1. And if we kind of back it up all the way to y naught, we can get a nice closed form, y sub k equals y naught times 1 minus h to the k. So this is a nice, straightforward way of how we can take a continuous differential equation and discretize it. Well, is the discretization, is it any good? Is it valuable? When is it valuable and when is it not? Here's some plots of the solution. Y sub k equals y naught times 1 minus h to the k. So remember we were talking about exponential decay. So you would expect the curve, the solution curve, to follow along this path, right? Just exponential decay. Now when h is equal to 0.5, sure, it looks kind of good. When h is equal to 1, it kind of just jolts down. You get this kind of sharp corner. Oh. And then when you increase h some more, you get these wiggles, which is not what you would expect when you discretize and you're looking for a decay equation. That does not look like a decay equation. When h is equal to 2, if you plug it in here, you get oscillatory behavior, which, yeah, you don't like that either. That's kind of like crap, right? And then you have this, it just kind of blows up, and that's just ridiculous. So there are certain intervals where the h works, gives you a valid estimate of what the solution looks like. And that occurs when the magnitude of h is less than 1. So the question is, can we do something else? This is my graduate student, Shay Adekanye. I have him do presentations. His thing is there something else that we can do to actually discretize so we don't get these oscillations or something that doesn't look like what the solution should be? So if we go back to the decay equation, this time let's consider dx dt is equal to negative lambda x with the initial condition x of 0 is equal to x naught. Well, again, we can have the solution x naught times e to the negative lambda t. Lambda is just a constant. Now, what we could do is we could take the top, the dx, the change in x, as x of k plus 1 minus x of k. But now we're going to do something fancy with the change in the time step. We're going to call it phi. Perhaps we can incorporate some of the dynamics of the equation into the change in the time step. So that if we make the phi dependent on h and lambda, h is the time step, and then lambda is the parameter that appears in the equation, if we choose phi to be 1 minus e to the minus lambda h over lambda, what happens if we substitute this down here, do some algebra and solve for the x of k plus 1, and simplifications, we get that x of k plus 1 is equal to x of k times e to the minus lambda h. What does that mean? As you go from x of k to x sub k plus 1, you're going to march along the solution curve. And we call this an exact solution. So here, we can compare the non-standard finite difference schemes using the fancy phi, which is shown here in red, against just the standard Euler scheme, which is shown here in blue. So if h is equal to 0.5, like we saw before, we get the exponential decay, which is what we expect. Here, if we actually have h is equal to 1, note that Euler, remember that has that sharp curve there, but the red dots, the non-standard finite schemes, they march along the solution curve. Similarly, we see when h is equal to 1.5, Euler is starting to oscillate here and settles, but these red dots, which is the non-standard, they go along the solution curve. So this is what we call an exact solution. So Renfrey-Potts posed a question. Given a linear ordinary differential equation, can one find a linear ordinary difference equation that has the same general solution? Meaning that whatever your h value is, can that difference equation exactly match the solution? So essentially, you can think of the difference equation solution as a proper subset of the continuous solution, because you're just picking like discrete points from the solution. So the ordinary difference solution set is a proper subset of the ordinary differential equation solution set. And they correspond at points t is equal to nh. And he says in his introduction here, in the vast subject of differential equations, one of the elegant features is the close similarity between the theories of linear differential and linear difference equations. So let's just briefly look at his paper here. So in this paper, he looks at a general first-order discretization. So we could write an ordinary differential equation as follows. So big D, you could think of that as dx dt. And m is just some sort of parameter. It could be complex, but you could also keep it real. Applied to x is equal to some f of t, where the f of t is maybe a forcing term. Perhaps there's a corresponding ordinary difference equation where you have this operator e. E basically maps x of n to x of n plus 1. And minus mu, and this is all applied to x of n. Mu is equal to e to the mh. And that equals to f sub n, where f sub n in this case is equal to e minus mu applied to y sub n. Now we can take this, why are we writing it this way? Because we'll extend it in the next slide, right? So we can take this ordinary difference equation and just rewrite it in the following way. dx dt minus mx is equal to f of t. We can solve for this, the homogeneous and the non-homogeneous, and toss them together. And we get x of t is equal to c sub 1 e to the mt, plus, and then here's your particular solution, y of t, right? Everybody loves differential equations, right? Okay, yeah. I heard there's just an exam, right? Okay, good. As long as we still love it and we're still saying yes, that's great. So here, y of t is a particular solution. We can, just use some simplification and write the ordinary difference equation as follows. X of n, so e applied to x of n is x of n plus 1. Remember, mu is equal to e to the mh times x of n. And then the right-hand side, we can substitute. We get y sub n plus 1 minus e to the mh y sub n. We can do some rewritings. And it's solved for x of n plus 1 here. And we get that x of n plus 1 is equal to e to the mh, c1, blah, 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 all those. So eventually, we get that x of n plus 1 is equal to c1 e to the mh times n plus 1 plus y sub n plus 1. Now, this looks so strikingly similar to the solution. So the ordinary difference equation and the ordinary difference equation have the same general solution. So we call this an exact difference scheme. They match up as again, it will march along the solution curve. He extended this to, let's say, a kth order differential equation. You can suppose that m sub i's are constants and they're different to make it nice. And again, we have the differential operator, but now we have this like product because it's a higher order. And again, we can do that same simplification of, we can rewrite the operator e as delta plus 1. Delta is the change. And the ordinary differential equation, after doing some algebra and dividing out, we could write it in this way on the left-hand side, where the denominator here, mu sub I minus 1 over m sub I, we say it's of order h, meaning that if you were to expand it out, it would be h plus some higher order terms, which kind of sounds like Euler. Order h, usually there's an h down there. You can think of this expression down here as a fancy h. But we also have that when the denominator goes to 0. And so note that in this case, the ordinary difference equation actually will converge to the ordinary differential equation. So how can we take some of these ideas and extend them to other equations? What's a nice, concise way to put it? Well, Mickens, in 1988, he said that if you suppose that you have a differential equation, if you know what the solution is, then by uniqueness, you can actually write out x of t plus h is equal to, here's your solution of x of t, comma t, and then t plus h. So if you know the solution, in theory, you can actually write the exact difference scheme. That may feel like cheating, right? You know, but okay. But he says if you know what the solution is, start there. Sometimes, well, oftentimes you can't find a solution if they're nonlinear. So we'll get to that in a moment. So the goal of nonstandard finite difference schemes is to maintain dynamical consistency. If you have exponential decay, you don't want wiggles. You want exponential decay if you discretize. So can you look at the system you're trying to discretize and incorporate some of those parameters and kind of perhaps fancy up the denominator, that h? We call that a denominator function, to incorporate some of those parameters. Or can you discretize some of the expressions, let's say, on the right-hand side, to achieve the dynamical consistency that you want? Perhaps you want non-negative solutions if you have population, right? Population shouldn't go negative. Or if you have some sort of bifurcation, maybe you want to see that in your difference equations. If you have conservation laws, perhaps you want to preserve that in the discretization. So there's a little bit of art kind of going back and forth and a bit of play. So the way we can think about constructing these non-standard finite discretizations is, well, you take the continuous t, and then you map it to t sub k, and it equals to hk, where h is your time step. So in this case, x sub t gets replaced by x sub k. One thing about the non-standard finite difference schemes is a non-local representation of functions, meaning that, let's say if you have x squared, you don't necessarily want to replace that with x sub k quantity squared. You might want to replace that with, instead of x sub k times x sub k, you may want to have x sub k times x sub k plus 1. You want to evaluate that expression, that nonlinear expression, over more than one grid point. Perhaps you get a better estimate that way. Is there more than one way to do it? Of course. So in this case, note that if the numerator is of an even power, perhaps, again, you could evaluate it at x of k plus 1 times x of k. If it's odd, here's one way to do it. You could evaluate it through this expression. But there are more ways to do that. So when you have nonlinear terms, perhaps you can kind of smooth it out and use different grid points to evaluate them. Denominator functions. So in the standard Euler scheme, the denominator is just an h. But again, in the non-standard finite difference scheme methodology, this h may get replaced by phi. It should be of order h, right? Because you want to maintain dynamical consistency, or else your stuff just goes nuts. And you want phi of h to be an increasing function of h. So it behaves like h, but it's not really h. It may depend on the parameters appearing in the differential equation. So you want to look at your parameter set and say, well, what sort of phi can I use? Here's an example of a nonlinear equation. This is the logistic growth equation. So in this equation, we have dx dt is equal to lambda 1x minus lambda 2 x squared, and we have an initial value. We can do our thing, whatever your thing is, separation, whatever, integrate, and we can get the solution, and we have this expression. So that's the solution to the differential equation. We should be able to find a non-standard finite difference scheme. That's exact. So here, if we replace the dx with x of k plus 1 minus x of k, replace this dt with the denominator function phi, on the right-hand side, how are we going to discretize that? We can replace lambda 1x with lambda 1xk, and that x squared we can replace with x of k plus 1 times x of k. That will give us the x squared. Well, what are we going to do with the phi? If we choose the phi to be e to the lambda 1h minus 1 over lambda 1, note that lambda 1 is the parameter of the linear term, right? So if we use the parameter of that linear term and have this expression, looks similar to what we looked at before for the decay equation. If we plug this phi back in here and do some algebra and things, we can solve for x of k plus 1, and we get this expression, which is directly similar to here. So note that when you have the continuous solution, obviously you start at x naught and you travel along the curve. In the discretization, you can think of, you start at x of k, you start at x naught, go to x1, x1, x2, x2, right, and you keep going. So this is an exact solution, and will actually march along that solution curve. So that's an exact scheme. So if we have nonlinear equations, how can we think about discretizing them? So here we have the dx dt is equal to ax, that's your linear part, and then this is your nonlinear stuff. Just as before, we looked at the linear part with that parameter, in this case a, and perhaps the denominator function should be e to the ah minus 1 over a. So this is a choice. It could be h, it could be something else, it depends on the system and how it evolves and the parameters that it has. But here's a way to handle nonlinear equations. You may also consider if you have some really messy or just a whole mess of equations looking at you, right? I don't know if you've ever been in that situation where you're like, what is this? You could take a proper subset of the terms and kind of ignore some, and then perhaps discretize those, and then bring it back to the bigger equation that you started with. So that's another technique. So I published a paper with Mickens on non-standard finite discretizations of interacting population models that satisfy conservation laws. So let's look at some of the examples that we constructed here. So the first law we looked at was the direct conservation laws. So let's say if you have a population, and the total population is P sub t, t for total, and you take your population 1, your population 2, all the way to population n, and that's your total population. Perhaps you're in a closed environment, and there's no change in your total population over time. It's 0. In this case, we say that the interacting population system satisfies a direct conservation law. Now, in full disclosure, Mickens is a physicist, so in my mind, physicists, they just love laws, right? You know, so we just go with it, right? It works for me. So in this case, the total population is constant, and here these are the initial values of the population. Can we discretize this and conserve this law? So here's an SAR model where we can think about a direct conservation law. This is called the SAR model. So S stands for susceptibles and diseases, right? Okay, y'all been in that classroom where somebody sneezes, you're feeling good, right? And then they sneeze, you're like, oh, come on, no, keep it to yourself, right? So the person that's sneezing would be in this infected block. And then if you're not sick yet, you're in the susceptible block. Now what happens is they may sneeze, you grab it, hopefully not, and then you then become infected. So we call these compartmental models because like you can think of people moving from compartment to compartment. Which compartment are you in? And then eventually maybe you sleep or what have you, or you do math and it makes you feel better, and then you moved into the recovered block, right? And so this is just a very simplified way we can think about the spread of infectious diseases. In this case, note that we have the change in your susceptible population with respect to time is equal to negative beta s times I. Well, why is it minus? Because when that person sneezes, you the susceptible, you're going to move into the infected category. So now you're going to have a decrease in the susceptible population. So it's minus. And I always say that populations get together, right? It's joint. They get together through multiplication. The more infected you have, the greater your chance you're going to move into the next category, and vice versa. And so once you move from the susceptible to the infected category, or maybe over some times or what have you, you sleep, you eventually will recover, so there will be a decrease in the infected population, and that will be an increase plus in the recovered population. And so that's a way we can think about the spread of infectious diseases. In this case, if you add up all the terms on the right-hand side, you get 0. So this satisfies a direct conservation law. How are we going to find this thing called the denominator function? Well, if we just kind of assume that there are 0 susceptible people, right? Everybody's infected initially. That's kind of a bummer, but let's just hypothetically assume that. Then I of t, the infected equation, satisfies di dt is equal to negative gamma I, which is similar. Well, that's the decay equation. And we know how to handle that in a non-standard way. We can discretize that with the phi here, phi being 1 minus e to the minus gamma h over gamma. And given that we have a conservation law, we would like that the change in population going from k to k plus 1, we want that to be 0 with some choice of the denominator function. If we choose this as the denominator function and we want this to be true, well, can we get that? Well, here, if we discretize in the following way, here we have the phi for each of them. It's the same for all of them. On the right-hand side, remember we had s times I, nonlinear. So we'll evaluate s at k plus 1, I at k. Note that the term gets repeated here. And then here we just have I sub k. If you add up the right-hand side again, you get 0. That's cool. So we have that conservation law is kind of preserved, right? And we can solve for the k plus 1 time step of each of them. And we can toss it into computer, code it up, and have fun, right? And so the denominator function phi is the same as before. So the conservation law holds. Note that on the right-hand side, there are no negative terms, and positivity of solutions is retained. Everything that you get for S, I, and R is not going to go negative. That's fantastic. What about this generalized conservation law? What is that? Well, if the total population satisfies this differential equation, meaning that changing your total population is equal to A1 minus B1 times the total population, A and B are non-negative parameters, then we have a generalized conservation law. For this equation, we could solve for it quite nicely, and we can get the solution seen here. And again, the initial total population is the sum of the initial populations that we have in the system. We also have that if we send time off to infinity here, this will, this gets knocked out to 0, and it will converge to a sub 1 over b sub 1. So when we discretize, we actually look at the equations. What properties does it have? What is it? Does it satisfy a law? Are there different behaviors that it's exhibiting? So here, let's consider the SAR model. So in this case, you can think about, again, hopefully you're unsusceptible, you're not sick. But then you're in that class and somebody sneezes, and they kind of infect you. But what happens, you enter into this exposed category. You don't know you're sick. You kind of go around, for the next 24 hours or what have you, feeling good. And then all of a sudden, wham, okay. Yeah, so it may take some time for you after you get exposed to then become infected. After you're infected, you could come back and be susceptible. And then here's recovered. Now the arrow's going out this way. That's like death rate, right? Okay, so here we can have the change in your susceptible population. Here we're going to have a birth rate, so it's just a constant b, so that's people being born, positive. Minus, now in this case, we're going to take the fraction of the infected population, and that interacts with the susceptible population as before through multiplication. And then this would be the susceptible population that's dying. This term gets replicated here because they enter into the exposed category. And then eventually, after some time period or whatever, you'll go from the exposed to the infected. And then after infected, you may go from infected to recovered. And here, note that you have the population is dying, right? The decay. I don't want to say the decay of a population, but the death rate, right, is exhibited by m times that population. So in this case, we have the total population as the sum of S, E, I, and the R. And this system obeys this generalized conservation laws if you add up all the right-hand sides. We also note that we would like to have the exact finite difference game to satisfy this expression. That looks similar to before. Maybe the denominator phi should be e to the 1 minus e to the minus mh over m. Will that work? Well, if we use that phi and discretize in the following way, meaning, so if we look at this nonlinear term, if we evaluate I sub k and over n sub k, if we evaluate this at the kth time step and this at k plus 1, we duplicate it down here, and we get a little fancy with it, and this evaluates at e sub k plus 1. But note that if you evaluate this at e sub k plus 1, you have to do the same here. Okay? If you discretize it this way, what happens is when you solve for the k plus 1 value for the S, E, I, and the R, we end up with non-negative solutions, which is great. Population doesn't go negative. And we also we preserve the Generalized Conservation Law in the discretization. The name of the game is, can you preserve the properties of the dynamical system into the discretization? So you're not just throwing it in some black box, some OD45, something like that. You're actually saying, can I construct something that would preserve behaviors? So that's one way we can handle nonlinear equations. So what about the bridge, right? The bridge over, I guess, troubled waters, maybe, I don't know. Maybe it was a troubled bridge. So this is the Tacoma Narrows Bridge in Washington State. Have y'all seen the movie on this one? Yeah, y'all seen, okay, it's not everybody saying, this is a weird movie. So they called it Galloping Gertie. It opened on July 1st, 1940, and it collapsed on November 7th, the same year. And people came from afar to actually drive over the bridge. I'm going to play the movie. I honestly probably would not drive over this bridge just because, I don't know, it kind of creeps me out. This is concrete, right? Would you want to drive over this bridge? I don't think so. But people came from a long distance to go over the bridge and experience the fluctuations. So this is on the day it collapsed. There's a car there, and unfortunately, there's a dog in the car, and they couldn't save the dog. This is Professor Ferguson running away from the car. He tried to get the dog, but the dog tried to bite at him, and the dog Toby lives on in the website. So Washington State actually has a website to honor Toby, the dog who died. Yeah, it's kind of wild. So the question is, what caused this bridge to collapse? Now, when you saw it oscillating this way, you saw sine and cosine. When you saw it go this way, you're thinking spring mass, where the spring are the cables of the roadbed, and then the mass is the road itself. So you're thinking spring mass, right? That's okay. Glad you were thinking that. If you were thinking something else, don't let me know. And I won't tell you what I was thinking. So, okay. So there was a lot of, here, I'm just going to trust the document always. There was actually a cat fight that broke out in the scientific community as to why the bridge collapsed. I mean, it got pretty nasty. I know you all think that all scientists are just loving, and no, this got really bad. So one of the questions was it resonance? Meaning that, okay, so you've been on that playground where if you push somebody on a swing at the right frequency, so you can think of the system as the swing going back and forth, then the swing, they'll go higher. But if you want to be a jerk, you can kind of when they come to you, you can kind of be off, and then they eventually stop, right? Okay, y'all are just nice people. These are my kids when they were this big. He's like 6'4" now, so this picture's kind of old. So there was a published paper in 1988 saying it was resonance. The wind matched that of the structure of the bridge. Now, people were like, how can periodic wind gusting be in tune with the natural frequency of the bridge? You've been on a windy day, and wind can be very variable, right? And so that would really require precise pressure variation, which, in all honesty, I don't think so, right? So that, even though it's a published paper, I don't think so. So because let's look at resonance here. So here, the cable, those are the cables on the bridge, and this M, that's the roadbed itself. And you can think of this as a spring mass just oscillating up and down. And you put some Hooke's law and some Newton's second law in there, and we can write a nice differential equation. So mass times acceleration is equal to the sum of the forces, right? So you have your damping, you have your spring constant with the K, and maybe you have some wind gusts here expressed by F cosine of omega t. I don't think so, but maybe you did. So this resonance occurs when this omega matches the natural frequency of the equation. Now, what does that mean? So here's a nice simple example. If we have this initial value problem, y double prime plus 4y equals cosine of 2t, with some initial conditions, we could write out the general solution. Note that the angles are all the same, right? So that you can think about the frequency matching. The frequency of this external is going to match that of the system. So if you were to plot this out, it would just kind of go wild. So this is their thinking that this is what happened to the bridge. But the wind, I don't think so. It's highly unlikely that the wind really matched the frequency of the bridge. So that's kind of, I don't know, maybe silly. I don't want to say that because I don't want somebody to yell at me, right? Yeah, because it got really crazy. Another question was this vortex shedding? So vortex shedding, this occurs if the frequency of the vortex shedding matches the resonant frequency of the structure. And the structure will begin to resonate, and the structure's movement can be self-sustaining. So you have these wind gusts of swirls that are just right to cause the bridge to go up and down. So engineers, Beeline and Scanlon, they claimed that the failure of the bridge was an aerodynamically induced condition of self-excitation, not forced resonance. So they were like, yeah, I don't think so, right, to the other people who published. Resonance between the bridge and these vortices caused excessive motion, destroying the bridge. So they were like, this is what it was. They were wrong. That movie's just going, isn't it? Okay. Okay. So there's a problem with vortex shedding. Theodore von Karman, I love Superwoman, what can I say, was an aeronautical engineer and calculated the vortex shedding frequency to be 1 Hertz. Professor Ferguson, the one who was running, observed a final torsional mode of frequency of 0.2 Hertz. 0.2, not equal to 1. So it being due to vortex shedding, I don't think so. So that was yeah. Doesn't take Wonder Woman to figure that out, right? So what was the real reason for the collapse of the Tacoma Narrows Bridge? Right, why did it collapse? That's the modern day picture now. Well, of course, a mathematician would save the day. So remember McKenna that I talked about at University of Connecticut? So that's McKenna. So hopefully he'll be okay with me superimposing him on Superman, right? So it was nonlinearity. Mathematicians, we save and figure things out. So he said that the explanation of resonance has enormous appeal in the mathematical and scientific community. It is plausible, remarkably easy to understand, and makes a really nice example. Resonance does not explain the bridge's collapse. The vortex shedding theory fails to explain the bridge's violent twisting. His claim was that the bridge had nonlinear springs, and this nonlinearity was not incorporated into the model. What does that mean? So if you have a cable, and if you have linear springs, that means that the force of the spring is going to be the same. It doesn't matter if it's stretched or in a compressed position. The force will be the same. If it's nonlinear, that means that, let's say, if it's compressed, you'll have one force, and if it's stretched out, you have a different one. Okay? Now, if you think about the roadbed, if it's compressed, yeah, sure, you're going to have gravity pulling on the roadbed, but there's not going to be as much force from the cables holding it up. If the roadbed is stretched out, the cables are really going to put a lot of force and yank it back up. So the force acting on the roadbed really depends on the position of the roadbed, let's say around equilibrium, right, around its resting state. So that's why if you have this one coefficient, maybe for y sub plus when it's positive, and the other one for when the y values are negative. So you have different forces, that gives the nonlinearity of the springs. So here's a picture, and so here's the roadbed. And note that the roadbed was going up and down, but it also had the torsional. So going up and down, we can call that y. That's your y of t, the distance going from equilibrium position to the roadbed. But then we also have that torsional motion that's noted by theta of t, going this way. We can use some physics, right? Some Lagrange's equations, kinetic energy, those potential energy, to come up with equations for acceleration, one for theta, and then one for the roadbed of the position of the roadbed. So note that we're going to have one behavior, one length when it's positive, and then we also have the other side here. And this is really, it's not linear at all. And if we assume the cables never lose tension, we can write y minus L sine theta plus as just that, meaning that it'll always be positive. There's always tension on the cables. When we make that substitution here, and add a small damping term, we can get the following expression, but we have this cosine and sine theta that appears. Cosine theta, sine theta, definitely not linear, right? So how would that impact if we were to discretize this and look at the computational output? Because I don't think we can find a solution there. So the question is, how does this system behave with the cosine theta, sine theta, versus this expression where you approximate theta being small? Remember, as theta goes to 0, cosine of theta goes to 1, right? Theta goes to 0, sine theta goes to theta. So we can, if we make that substitution here, do this approximation, do we still get the same behavior, or do things really change? Does it really matter? Well, if we look at the torsional motion, theta of t, the linear versus nonlinear, they actually found wildly different behavior. So the output is that it really does matter if you keep nonlinear terms in your equation versus linear terms in your equation. At the time when they were doing these calculations, we didn't really have the full power of the computer. So in all honesty, linear expressions were much easier. But later on, we get more power with the computer. We can do more and handle nonlinear. Back in 2007, a former undergraduate student that I did a research project with, he looked at, well, what happens if you vary the wind or vary the external forcing term? If the external forcing term did this, what would happen to the system? So he looked under different expressions, as complicated as he'd love them to be, to figure out, well, what happened in the rotation of the bridge. And he published this in the Rolls-Holman undergraduate journal. It was interesting. So he was a civil engineering student. And when I said, apply to grad school, he only applied for master's. I said, no, do PhD. It'll be fine. And so they actually called him back and said, you need to apply for PhD. So he actually ended up getting his PhD in engineering. So as an applied mathematician, I tend to work with students in different disciplines: math, physics, engineering, chemistry, atmospheric, whatever. Everything's math, right? So what's a way we can discretize the Tacoma Narrows Bridge in the non-standard sort of way? We can take this nonlinear instead of the plus and the minus, and then use this super nonlinear function f here in these expressions. And similarly, the equations as before. What sometimes we like to do when we discretize, we like to take a second-order equation and turn it into a system of first-order equations by a reasonable substitution. So if we let y prime equal to w and theta prime equal to v, well, then we can rewrite this y double prime as, well, obviously, y prime is w, right? And then if you take the second derivative and then just replace the terms on the right-hand side with either y or w. So we can rewrite y double prime as a system of first-order equations for the vertical motion. And then similarly for the torsional motion, we can write that as a system of first-order equations. Now, if we were to discretize this in the standard way, you just kind of Euler your heart away. And you just do y sub k plus 1 minus y sub k over h. Similarly for the rest. And then toss in your y sub k's, theta sub k's, w sub k's. Everything sub k is on the right-hand side. Right? That's the standard Euler. But what if we wanted to do the non-standard way? So remember a long time ago in this talk, I said, why don't you look at the linear term? So perhaps you could take a system, maybe find the Jacobian or pull out the linear term in some sort of way, and use that as a basis. If we look at a system of equations with constant coefficients, perhaps we can find the exact solution there. So note here we have a psi, which is the equivalent to the denominator function. And if we choose psi in this way, well, psi in this way and phi in this way, all these Greek letters, you actually do get an exact solution. You could almost think of this as an extension of the equations, the decay equation, the equations we looked at before. So in this case, if you take the nonlinear equation, find the Jacobian, meaning the linear approximation plus there would be some higher order stuff there. But that linear part, discretize it as before with the denominator functions, we actually get some really interesting results. And note here on the right-hand side, we have some y sub k plus 1s and theta sub k plus 1s. And some of this is teased out through play. The top-hand side, OK, so the top, we have the output if we use ODE 45 in MATLAB. ODE 45 is just Runge-Kutta using like a 4-5, right? Predictor corrector method. So why do we use that? Because we don't have an exact solution. It's not linear. So it's like, well, how good are we? So we use that as a comparison. So the top graph is the vertical motion. Again, you can think about the bridge going up and down. And the second one is a torsional motion. That's the twisting. So if we use Euler, we have this pretty purple, but the purple's pretty, but the shape of the purple is not so pretty because it doesn't really match. And pretty is a function on MATLAB. That's why I like MATLAB, right? And you can also have the torsional motion here, which, yeah, that doesn't match at all. So if you use the same time step and the non-standard, do you actually preserve? Is it any better? Well, for the non-standard finite difference game, if using the same time step, you actually preserve the solution for the vertical and the torsional. So the hypothesis is that by preserving the characteristics of the dynamical system, the differential equations you're discretizing, you actually will get a better result. And you don't have to be so picky about your time step. They can be wider, which may save time, computational time. So standard finite difference schemes, they're quite different from non-standard schemes. So remember Taylor polynomials? You ever sat there and was like, what that, why, right? Well, let me tell you why. Taylor's a good dude, right? And hopefully you all will get your own Taylor series and polynomials here, right? Okay, so for the standard finite difference schemes, they're all grounded in Taylor, all of them. You just Taylor your heart away. And that's what you use to do the analysis of how good it is. Is one better than the other if we're looking at order, or sometimes in constructing them. These standard schemes tend to be black boxes, meaning you just have an equation, you toss it in, and hopefully you get something good out. You know, nothing too stiff or too crazy, right? But yeah, there may be some other techniques you can use. Non-standard schemes, they actually look at each differential equation uniquely and say, what are the properties I'd like to preserve, and how can I embed those in the discretization? So there's a bit of interplay, understanding of what the equation is that you want it to model, and then discretizing it. And that's dynamical consistency. So non-standard finite difference schemes, they're grounded in, is it dynamically consistent? Standard finite difference schemes is grounded in consistency, stability, and convergence. So they're two different treatments and discretizing, but they're quite different in what they're looking for and what they call as a good or a best. So, you know, in doing this math, this is just a screenshot of doing these equations. It's really fun to be in the mathematical community. Here, at that time, we were governesses. I liked being a governess because I think it sounds cool, with the MAA. And then here I am with NAM, and here I am with AMS. He's the former president. You know, got to do the selfies with the photobomb there. And then here I was doing outreach with students with an AWM chapter, Association for Women in Mathematics. And then I've also been involved with SOCNAS, and that's me right there. So in doing the mathematics, I always found that it's fun to do it with other people. That's just the kind of person I am. I like to, go to workshops, figure this out, sit down with other people. Maybe it's because I like to argue. So then we can argue about the concepts, right, and coalesce it into something bigger and greater. So with that, I just want to end with the Chinese proverb, the journey is the reward. So this is a picture here of a session that we did at the joint math meetings. This is when we had the snowstorm in Atlanta. And we had a session on non-standard finite difference schemes. So it's great to be in a community with other people who are all over the country. He's in Texas, he and him, they're in South Africa, he's in Arizona, he's in Delaware, he's in California. Everybody's all over, but we're so interconnected because our research really coalesces and just comes together in a nice, neat way. So with the end, I'll take some questions, but just remember, the journey is the reward. Thank you.
Questions for Talitha? You have a question?
Yeah. Okay. Thank you much. My dissertation had the word non-standard in it, but it was non-standard analysis back in the Middle Ages. So is that connected at all to this? It doesn't sound like it.
Define what you mean by non-standard analysis.
Where you take a different, instead of the reals, you augment them with infinitesimals.
So real numbers.
So it's kind of like you're doing something different than what other people typically would do, right? And I say typically very loosely, right? Because when people think of finite difference schemes, they immediately go to a thought, right? So I think this is why they call those standard, right? But the non-standard ways are you really look at the equation that you're want to discretize and kind of construct It's discretization. So it's, I hear what you're saying, that is it a misnomer? I don't know. But when you think of finite difference schemes, people think of Euler, grounded in Taylor, you know, Runge-Kutta, whatever, predictor corrector, all these fun things, Adams, Barefoot, you know, whatever. But the non-standard, it's quite different. And it's not the standard way that would be employed, let's say, in MATLAB and the ODE solvers. So it's non-standard in that sense. I'm not sure, if you can think of a better way to call it, that would be great.
Other questions? Oh, sorry.
Hi, thank you. So I think I missed this at the end, but early on you came up with trying to find the denominator function, and you built it off of the known solution to the differential equation. How might one go, and I think you just need to re-summarize for me, how do you go about that if you don't know the solution to the differential equation?
Well, what you can do is you can, one way, right, there could be more than one way, is to look at the linear part of the system, let's say, and use that. You're basically kind of knocking out the rest of the variables, looking at just the linear part that you know the solution to, and you can build it that way, right? Or let's say if you don't have any linear terms, perhaps you can do a linearization, right? So remember back in Calc 1 when you had to find the equation of the tangent line? Same idea, but for a system. So you approximate the system with a linear approximation, maybe through the derivative, the Jacobian, or what have you, and you can use that to find the denominator function and then take it back to the bigger system. But you don't want the time step of your denominator function to be too big, because you have time steps that may be embedded into the parameters of the system, and you want to make sure that you capture them. So you always kind of want to be less than, let's say, the time steps, the time that's already in the system. Does that help?
Yes. If I understand you correctly, then, if you have the exact solution, then the difference equation values will track the exact solution. But when you use the approximation techniques, the values for the difference equation are not going to track the exact solution exactly, but you're going to maintain key properties.
Exactly.
Okay.
Very well said. Yes, exactly.
I have a question too, if I may.
What impact have this increasing understanding of what led to the Tacoma Narrows Bridge collapse had on the development of the design of bridges?
That's a good question. You know, I always say that engineers built the bridge that collapsed and mathematicians figured out why, right? So bad. Yeah.
I mean, the obvious thing is you need linear springs, right? I mean, is that, if that's possible, but.
Yeah, no, yeah, you're right. So linear springs in what sense, right? So essentially, you want to bring back the linearness, maybe, to the springs. So you want to have the force to pull it down when the road bed gets compressed, right? So you want to have that same force. So that's kind of what they did. They rebuilt it, but then just clamped it down so you wouldn't have that, it wouldn't be so flexible, let's say, going in the upward direction to balance out the forces in the compressed and then the stretched. So yeah. I think they just did it naturally, but that, yeah.
So a question not just for you, but for anybody. I wonder how many other Tacoma Narrow type bridges are out there that were designed in that same period with that same approach.
Well, there was the Golgograd Bridge in Russia that oscillated. Yeah. So there are bridges that will have this oscillating, and then you have the bridges where you have the marching soldiers and the resonance of the marching that causes the bridge to kind of wiggle. Or, you know, if you ever go hiking and you have those trails, you know, you're kind of on this little platform holding onto the ropes and people are walking, you're kind of, yeah. So you can kind of think of the resonance matching that of the structure. Yeah. Kind of creeps me out, but yeah.
Other questions?
This isn't really a question, but I've also heard a story of like a building was built and there was a yoga class on one floor, and another floor higher up had thought there was like an earthquake going on because the yoga class had hit like a resonant frequency.
Nice.
And they like called the police and everything, and it was an ordeal.
Yeah, well, these structures, they have a resonant frequency, and can you match them to actually get them to move? Yeah. You know, that'd be a fun yoga class to take, right? Namaste, yeah.
So one more question, for now anyway. To what extent do these premier CAS programs like MATLAB or Mathematica notify you if it's likely that the solution that they're showing you in some numerical approximation solution to a DE is not really representing reality? I mean, should I trust what I see, or is it going to get flagged, or so forth?
So yeah, so how do you know that what you get is what you get? You know, right, exactly. There's a bit of intuition that has to go in, because if you tend to use the black box programs, you have to really know kind of what that black box is doing and what it cannot do, what the limitations are. And you want to have an idea about what you expect the solution to look like. Because if you don't kind of have that intuition, if I change this, maybe, you know, if I change the step size, does the solution change by a lot or a little? Are there different ways you can kind of play to kind of feel out, is this really what I have? So I actually, like for Runga Code 4.5, I have my students kind of code it out all the way. Then you can use it. So I'm like, code it first, then you can use it. Because then you really understand, well, all the joys and the pains of doing it, but you also understand exactly what that program is doing. So if you can code it and then you can trust the black box, that's good. You have an idea about where to go. Like with MATLAB, there are papers. So if you look up the solvers, there are research papers that they base it on, the solvers. So sometimes it's good to kind of bring that into the discussion. How do they really solve this? What are the nitty-gritty details? And actually, in I guess like next month, MATLAB has these research symposiums, and I'm going to go to it. So to bring researchers together to kind of bootstrap up the programs to really meet the needs of the field. I remember when I was at Howard a couple weeks ago, one of my colleagues, Katie Gursky, was like, you know, I wanted this exact functionality in MATLAB. I don't remember exactly what it was, but she was like, I said, well, just tell them. She said, and now they actually have it. So MATLAB and Mathematica, they do have that interplay where I feel like, you know what, I really need this functionality. If you let them know, more often than not, they'll incorporate it. So it's very dynamic.
Are the dangers that all these solving routines are becoming proprietary and not open source? I mean, like I have Mathematica solve something and it solves it, it's great. It matches my black box, my intuition, but I don't know how it did it, so I can't replicate it on my own. What do you suggest?
There should be, like, so I often do more in MATLAB. And with the MATLAB packages, there are papers associated to it. They're very clear about, you know, like they'll have, like, this paper appeared here, and that's what this discritization is based off of. So you could actually go in and replicate and get the exact same thing. You know, minus computational error sort of thing.
From that sense, it's kind of open source.
In that sense, right. Because I think that for MATLAB and MathWorks really to be viable and to interact with the community, you know, we're kind of skeptics, right? And so they really have to be open with, you know, this is how we're finding it, this is what we're doing, and we're here to make your life easier, so give us some money, right? So there has to be trust on both sides.
Because sometimes I see Mathematica evaluate integrals, and it's just like, I have no idea how they got to this. They're using some theory that's way over my head. And it would be nice to know that theory, but it's proprietary.
No, I don't think so. At least with the MATLAB that I've actually looked up, you can actually see how they approximate. After a while, you're like, okay, fine. You know what I mean? You may not dig deep into it, but you kind of get that, you get a nicer familiarity. But now they have a lot more like app type stuff in the programs, which is kind of interesting. And my students kind of bring me, because I'm kind of old school, but there are apps that you can get that will actually discretize things in a really nice way with way more computational power. And I think they're pretty fancy. But I think also at the same time, they do keep the information updated as far as why and how. It's good online resources for libraries looking into that.
Okay, I'm going to give Sunil the last question here.
Yeah.
Sorry if I missed this. So this seemed to be all engineering sort of oriented. Did you have any favorite application of this sort of methodology to non-engineering problems? Like, because you said you've worked with varying fields. Have you applied this in other?
Part of infectious diseases?
Sure, and then, sorry, yes, I guess other than the two, because I guess I was most interested you said that you've worked with chemists and sort of that sort of field.
Oh, okay, so what did I do with the chemists?
Yeah.
Yeah, so I called it data science on the beach. It was in Puerto Rico. Yeah, it was really fun. So, so if you're a chemist, right? So we're thinking like atmospheric chemist. You may look at dust particles that start in sub-Saharan Africa and travel. So the whole idea of where these dust particles are using geostatistics, the lat and longitude data, could be very helpful. So what I do with the at least atmospheric chemists is looking at how to do this thing of geospatial modeling with lat and longitude. So you can kind of figure out where things are. And you can create graphics to really help explain the story you want to project about what's going on. So my students, they tend to love data science, and I tend to be a sucker for learning. I'm like, yeah, sure, okay, we'll do it. So they've drugged me by the ear to do more in data science. And then, so I've taught like courses in it with my colleague who does geometry. I said, don't worry, we'll just have fun with this. So what we usually do is, what we did for a semester is, it was an hour-and-a-half class, but they got an hour credit. So it's kind of like a lab-based. It was teamwork. It was advanced undergraduates and beginning graduate students who weren't even all applied math people. But we were given we worked through different data sets in a team-oriented environment where we can kind of say, okay, this is the data. How can we use like different tools to say something about the data? And that could be from either geospatial modeling, running some tests, or what have you, right? And so that tends to be a lot of fun. And now I find that my students, what do? They go off and find these jobs in data science. It's very good, high paying. You know? So I guess as of late, I've played around with geospatial modeling. I remember I did a workshop at SAR, but it was on predictive policing, and I looked at the call volumes. And so, I had a geospatial model, and I was like, I wonder if this is any good. So I did what any good mathematician would do. I took my geospatial model picture, and then I Facebook messaged it to a friend of mine who's a statistician. It was like, is this any good? Monica Jackson, and she's like a geospatial modeler, and I'm just like, yeah, you're great. And she was like, oh my goodness, this is exactly what I do. I was like, oh gosh. Because when you come into a new field, you're not really sure where the parameters are. So I've been validated, right? Yeah. So I've been kind of just a sucker for learning. If you see this phenomenon or you have this information, how can you use mathematics to determine or say something about what's going on? If either that's using dynamical systems or some data science techniques, geospatial modeling, what are the different tools that can be used to make sense of what's happening in the world? In this case, a nonlinear world.
Thank you very much for introducing, well, for me, speaking for myself, a new twist on an old problem. So thank you very much. And thank all of you for all of your contributions for making this a terrific mathematics weekend. Please drive safely. Keep your eyes peeled for next year's Pi Mu Epsilon conference speaker to be announced, correct? Okay, not quite settled yet. So, thank you all again for coming.